number 40, and it is the same directions, which is to turn this into polar form. So we have r cosine square of theta, well, not yet square, but cosine theta all squared plus r sine theta all squared equals to 16. So since these two are being multiplied, we can easily say r square cosine square plus r square sine square of theta is equal to 16. Factor out the r square, and we have cosine square of theta plus r sine, just sine square of theta. All of that is equal to 16. And this right here is a Pythagorean identity, so we have r squared times 1 equals to 16, and then r equals to 4. Number 41, we're going to change the equation from rectangular coordinates to polar coordinates. So replace the x with r cosine theta and the y with r sine theta, and plus 14 equals to 0. So what we can do is factor out the r. So we have r times 8 cosine theta minus 7 sine theta equals to negative 14. So r is equal to negative 14 over 8 cosine theta minus 7 sine theta. Okay. Next we have converting the polar coordinate or the polar equation into a rectangular equation. So for number 42, we know that r is equal to square root of x squared plus y squared. So we can replace that with that information and say this is all equals to 8. X squared plus y squared equals to 64. And that's it. This will be the equivalent rectangular equation for r equals 8. Okay, now theta equals 5 pi over 4, so we can figure that out using the tangent function, which is tangent of theta is equal to y over x. So whatever tangent of 5 pi over 4 is, 5 pi over 6, and we get something like square root of 3 over 3, but negative, and that's equals to y over x. Therefore, if you multiply to the other side, you got negative square root of 3 over 3 times x equals to y, and that would be the rectangular equation that matches that polar coordinate equation. Okay. Then, if we continue, we have r is equal to cosine theta. Well, we know that, and this is number 44. R is equals to r equals x cosine theta. So if I replace r with that, I have x cosine theta equals to negative 7 cosine theta, and if I divide both sides by cosine theta, then I have x is equals to negative 7. And that will be the rectangular equation that matches with that polar equation. Okay? For number 45, we're going to be very creative because there are different ways to go about it. We know some definitions like r squared is equal to x squared plus y squared. We know that x is equals to r cosine theta, y is equals to r sine theta. So those three can be seen as identities or definitions that we know for going between rectangular and polar coordinates. So that being said, let's try to focus on number 45 and multiply both sides by r. So if I multiply the left and the right side by r, we'll get r squared is equal to 6 times r cosine theta plus 2r sine theta, and that's probably the quickest way to do it, since on the left side we can plug in the definition x squared plus y squared is equal to 6x plus 2y. Right away we get rid of the r in cosine and sine, and I mean pretty much we can stop there or try to rearrange things in such a way where things are next to each other in some way. Okay, probably the best that we can get. Okay, number 46, when we're trying to plot complex numbers, right? Remember that we're no longer thinking of our x and y system. We're thinking of the real axis and the imaginary. Okay, where this component is the real component and the second component is the imaginary. Okay, so in this example that we're trying to solve, we have the number 3 plus 6i. The whole thing is one number, and so we go to the right from the origin, 3 units to the right, and then 6 units up in the imaginary direction. Therefore, the point 3 plus 6i is right here. Okay, so this is 3 plus 6i, and that's how we graph or plot that point. Okay, next, number 47. When we're talking about a number that has no real component, right, we can view it as 0 plus 4i, right? That's a complex number and its real part is 0, meaning that if I start on the center 0 0, I don't go left or right, I just stay there, and I go upwards 4 units right here. So therefore that is my point 4i. Okay, number 48, we're still trying to plot the complex number, and so we start at the origin, and if we go left 5 units, because that's the real part, negative 5, and then I, just the number that's in front of the I is 1, will be right here. So this is the number negative 5 plus 1I. Okay? Find the absolute value of the complex number. So the number z for definition has the component a plus bi, or the definition of it is just a plus bi. And if we are talking about finding the absolute value of it, it just means finding the magnitude of that number, or a square plus b square. Okay, so in this case, we take the square root of 20 squared, which is 20. Okay, and if you don't remember, think about the point here, a plus bi, and we're finding that diagonal. That diagonal right here is the magnitude or the absolute value of it. This is the a, and this is the b distance that we have to cover. So in order to go from this point at the origin to the point a plus bi, we take the a square and b square, and that'll give us z squared, but z is the square root of a squared plus b squared, right? So that's where that comes from. Here, we're taking the absolute value of it, or the magnitude. It'll be square root of 9 squared plus 15 squared. 9 squared or negative 9 squared give us the same thing, so it's okay to not use the negative. But if we do use it, make sure you put it in parentheses. So when you put in your calculator, it gives you the right answer. And we get something like, let's say, square root of 306. And perhaps we could leave it like that. Unless we can factor it out between two perfect roots. Once again, taking the absolute value of this, and perhaps we can't simplify it, so we'll leave it as it is. Okay, number 52, we want to write the complex number in polar form and express the argument in degrees. So that means that 4i is the number that goes straight upwards to 4i to 4 units upwards. Now, the way we do or find the equivalent polar expression of it is that we have r is equal to the magnitude, right? Or z is equal to the radius, right? And that is going to be the components squared, right? The sum of the components, or the components of the complex number. So in this case, we have the radius to be 4. So r is equals to 4, and theta will be tangent of theta equals to a, more exactly would be b over a, where a will be the value of b. In this case is 4. Now the problem is that it's going to be undefined, right? Because this will be 4 over 0. And we cannot divide by 0. Therefore, it's going to be undefined. Now, where is tangent undefined? It's undefined at pi over 2 and 3 pi over 2, right? And since we know that the angle is 90 degrees, then theta is 90 degrees, right? So this expression of 4i is equivalent to 4 times cosine of 90 plus sine of 90 degrees, right? And when it simplifies, we just get 4 times sine of 90, which is 1, and it just gives us 4. But in order to leave it in polar form, we just keep it with the sign there, okay, without evaluating. And remember, sine has the I that goes with it. Should have said that from the beginning. Cosine is the real component, and then sine gets the I, or the imaginary component that goes with it, okay? Okay, next, let's figure out this one. It has both components, the A and the B portion of it. So let's figure out the radius, and the radius is going to be the 3 value squared plus the 4 value squared, right? So we have 9 plus 16, which is 25, and the square root of 25 is 5. Okay, so that's the value of the r. Then let's find the angle, and that's b over a. So tangent of theta is equal to 4 over negative 3, right? So theta is equal to tangent inverse of negative 4 over 3, and let's see. Since we're doing it in degrees, then we get a theta being approximate to negative 53 degrees. So if we want to put it in positive degrees, it will be 307 degrees, right? So actually, take it back, since that point is on the second quadrant, right? So be careful and try to get the reference value for that, okay? So this point right here tells us that the theta that is inside of the triangle, or the inner angle, is 53 degrees. So we have to do 180 minus the 53, okay, or the absolute value of it, which gives us 127, right? So that being said, let's go ahead and finalize the solution for this. So r is 5, and so 5 times cosine of 53 plus I sine, should be 127, right? And that will be our equivalent expression in polar form. Okay. Number 54, let's go ahead and convert that complex number into a polar form and express the argument in radians, right? So instead of degrees like we did in the previous one. So again, let's figure out the radius. So radius is 2 squared plus negative 2 squared, and that gives us the square root of 4 plus 4, and that is the square root of 8. Again, the radius is the sum of the two components, each one of them squared. Then, once we have the square root of 8, we're going to simplify it a little bit, and hopefully we can see that this is equal to 2 square root of 2. So, the radius is 2 square root of 2. Now, since that point is on the fourth quadrant, meaning to the right and down, we're going to do tangent theta of the b value over the a, so that means negative 2 over 2, which gives us negative 1. And so when we take the inverse of it, we will get what do we get? So tangent inverse of negative 1 is going to be negative 45 degrees, or 315. Okay, so that would be 7 pi over 4. Okay, so 2 square root of 2 times cosine 7 pi over 4 plus I sine 7 pi over 4 will be the equivalent equation in polar form with the argument in radians. Number 55, we're going to write the complex number in rectangular form. So we're still going to have a complex number, just not in polar form. So what we do is evaluate cosine of 225 degrees as well as sine of 225 degrees. Now, once we get the value, we're going to do negative 3 times negative square root of 2 over 2, which is cosine of 225, plus I, or really minus square root of 2 over 2 times I, because sine of 225 is also negative. So once I distribute that negative 3 into everything, I will have the following: 3 square root of 2 over 2 plus 3 square root of 2 over 2I. And that will be the equivalent rectangular form of that equation. Okay? Then the following, let's evaluate or write the complex number in rectangular form of 9 times cosine of 2 pi over 3 plus I sine of 2 pi over 3. So let's figure out cosine of 2 pi over 3. Okay, so again, let's evaluate this, and that value we have 9 times cosine of 2 pi over 3 is negative 1/2 plus sine at 2 pi over 3 will be positive square root of 3 over 2 times I, and once we simplify that, we'll have negative 9 over 2 plus 9 square root of 3 over 2I. Okay, so just double check and make sure that we have the correct values for sine and cosine. Okay. Next, we want to find the product of the complex numbers. So notice that we have two complex numbers, z1 and z2 are going to be the distinct complex numbers. Before we start, let's remember what the formula for multiplying the two complex numbers is. If I have z1 times z2, it is equal to r1 times r2 and times cosine of theta 1 plus theta 2, meaning the argument angles that we have there, plus I sine of theta 1 plus theta 2. Okay, so that is the formula for it. So if we carry out that product, we have 6 times 4, and then inside of the argument we have cosine of 36 plus 6 plus I sine of 36 plus 6, which leaves us with 6 times 4 will be 24, and then inside of the parentheses or inside of that square bracket we're going to have cosine of 42 degrees plus I sine of 42. So the product between z1 and z2 and number 57 is 24 times cosine of 42 degrees plus I sine of 42. Okay, so hopefully that makes some sense, and working with degrees is fairly simple. All you have to do is multiply the two radiuses and add the degrees, right? So adding the degrees is not really too complicated, but as long as we know the formula, we should be alright. Okay, number 58. Same deal, except now we have radians in the argument. So let's go ahead and multiply the two radiuses. Then we have cosine of pi over 4 plus pi over 6 plus I sine of pi over 4 plus pi over 6. Okay, so that is the setup. Then 6 times 7 is 42. Now, when we're adding those two, we need to get common denominators, right? Because 4 and 6 are not the same, so we have to get a common denominator. So we will have 6 pi over 24 plus 4 pi over 24. We'll have the same for the arguments in sign. Okay, so let's simplify a little bit more. Okay, so we have 42 times cosine of 10 pi over 24. So if we have 10 pi over 24, we can divide both by 2, leaving us with 5 pi over 12, and that doesn't simplify anymore, plus I sine of 5 pi over 12, and that should be our final expression. Number 59, we're trying to find the quotient. So find z1 divided by z2, and we're asked to leave the answer in polar form. So leave in polar form. Okay, so z1 is given as 5 times cosine of 200 degrees plus I sine of 200 degrees. Okay, z2 is 4 times cosine of 40 plus I sine of 40 degrees. Correction. It is 50 degrees for z2. Okay, so what we do is that we use the formula for when dividing two numbers in polar form. Okay, so two complex numbers in polar form, and it is the following. So the first radius divided by the second radius, all of that multiplied by cosine of the first theta minus the second theta plus I sine of the first theta or the first angle minus the second angle. Okay, so that is the formula we're going to use for finding out the quotient of two complex numbers in polar form. So let's go ahead and do that. z1 divided by z2 will be given by 5 over 4 times cosine of 200 minus 50 plus I sine of 200 minus 50, and all of that it's inside of the parentheses. Then we have 5 over 4 times cosine of 150 plus I sine of 150. And we are done. Okay, this right here is the final answer, and it is in polar form because it consists of cosine and sine. Okay, if we were further simplifying, then it would become rectangular form. So we can stop right there. Okay. '60 is, once again, finding the quotient between the two complex numbers. In this case, we got z1 equal to 8 times cosine of pi over 2 plus I sine pi over 2, and z2 is given as 3 times cosine of pi over 6 plus I sine pi over 6. Okay, so z1 over z2 is given by 8 over 3 times cosine of pi over 2 minus pi over 6 plus I sine of pi over 2 minus pi over 6, and all of that inside of the parentheses. Okay, next step will be to simplify what's inside of the parentheses. So we still have 8 over 3 outside of the parentheses, so 8 over 3 times cosine of, we need to get some common denominators, so pi over 2 can be the same thing as 6 pi over 12 minus, and then we have 2 pi over 12. Okay, the 12 will be our common denominator. So let's rewrite the rest of the problem so that it reflects the same common denominator. Okay, so 8 over 3 times cosine of 4 pi over 3 plus I sine of 4 pi over 12. And then 8 over 3 times cosine of pi over 3 plus I sine of pi over 3 is our final answer, and that is in polar form. Okay, so that is finding the quotient of complex numbers. Number 61 is asking us to use DeMoivre's theorem to find the indicated power of the complex number. So 61 is the following: cosine of 30 degrees plus I sine of 30 degrees, and this is all to power 6. So the final answer should be in rectangular form. Okay, so let's go ahead and write the theorem or the definition for finding a power of a complex number. So any number z, complex number z, is equal to r times cosine of theta plus I sine of theta, and all of that is to the power n. That is all equal to r to the power n times cosine n times theta plus I sine of n times theta. And remember, n is the power that we're raising the whole number to. Okay, so that is the definition. So let's go ahead and do that. So, you know, there's a 1 out in front. So 1 to the power 6 times cosine of 30 degrees times 6 plus I sine of 30 degrees times 6. So that is all that's inside of the parentheses. Well, 1 to the power 6 is just 1, or we don't have to write it. And then inside we have cosine of 180 plus I sine of 180 degrees. Next, we're going to evaluate cosine at 180 degrees, which gives us -1 plus I times 0. Overall, then, this is -1. So this complex number, we'll call it z, in rectangular form, and it's our final solution, is equals to -1. Here is its polar form. Okay, so that step between polar form and rectangular form is a conversion between one and the other. Okay, number 62 is the same thing. We're looking for the power, right? We're raising this complex number to some power, and in this case we have cosine 3 pi over 4 plus I sine of 3 pi over 4, and all of that to the power 3. So once again, we want to leave the answer in rectangular form, just because those are the indications of the problem. Okay, so let's go ahead and go with it. So we'll say that this number is some number z. So z to the power 3 is equal to 10 to the power 3 times cosine of 3 times 3 pi over 4 plus I sine of 3 times 3 pi over 4. So that is all inside of the parentheses. Next, we simplify. 10 to the power 3 is 1000. And then we have cosine of 9 pi over 4 plus I sine of 9 pi over 4. Okay, so at this point we're ready to figure out the conversion, right? Right now we are in polar form, and we could have left that as our final solution if the indications didn't say that we needed to leave in rectangular. Okay, so 9 pi over 4. Let's try to figure out 9 pi over 4. So here's my unit circle, and I'm going to break it up into quarters. So here's 0, 1, 2, 3, 4, 5, 6, 7, 8, and pi over 4, it is the same thing as pi over 4. Okay, so cosine at pi over 4 is the same thing as cosine of 9 pi over 4. So 1000 times square root of 2 over 2 plus I times square root of 2 over 2. Okay, so then we distribute the 1000 inside of there, and so we have 1000 square root of 2 over 2 plus 1000 I square root of 2 over 2, and we can simplify that to 500 square root of 2 plus 500I square root of 2, and this is in rectangular form. Okay, at that point we have completed the complex number being raised to a certain power. Now we're getting into the vector topics, right? So number 63, find the magnitude, and that is the symbol for finding the magnitude, right? The double bar. Okay, so find the magnitude of the vector. So that we can do fairly easily. Let's see. Think of this as being a vector, and this is the I direction and this is the J direction, right? So this vector goes 6 to the right and then 8 down, so something like that, and then here is this vector. We want to find its length. Now its length is given by the square root of the value that's in the I component, so a squared plus the value that's in the J component, or the coefficient. Okay, so let's do it. So magnitude of V is equal to square root of 6 squared plus 8 squared. Remember, you can do negative 8 as long as you keep it in parentheses, and it'll be the same thing. So 36 plus 64 gives us 100, and when we take the square root of it, we get 10. Therefore, the magnitude is 10. So 6, 8, 10 is another Pythagorean triplet. Okay. Cool. Next, the magnitude of the vector v in number 64. So negative 2 squared plus 2 squared, which gives us square root of 4 plus 4, which is 8. And then if we simplify, we get 2 square root of 2. Okay, so the magnitude of the vector negative 2i plus 2j will be 2 square root of 2. And then the magnitude of the vector with both components being negative, or just negative 1, I, or negative I minus j, will be the following. Square root of negative 1 squared plus negative 1 squared gives us square root of 1 plus 1, which is 2. And the magnitude then will be the square root of 2. Okay. On number 67, we're asked to draw a sketch to represent the vector sum. Now, whenever we're doing a sum, all that we have to do is start out with the first vector given, which is v. So v looks something like that. And on the head of it, we're going to put the tail of the second vector. So vector c will start right here and goes like that, something like this, right? Now, then we use the triangle form, or the triangle method, to draw the resultant. So the resultant is this, right? That diagonal piece, therefore this is b plus c. Okay, maybe a little difficult to see. This would be the resultant, right? Something like that, okay? Next, we want to figure out number 68, which is 2d minus a. Now, this is saying twice the length of d. So here's d, that's 1, and then another 1. Okay, so that would be 2d. Then we're taking away a, which is the same thing as adding a negative of a. So if we're adding a negative of it, let's see, how can we best do this? It would be pointing downwards. Okay, so this is 2d and this is negative a, and here is the resultant. Okay, so this would be 2d minus a, or just an addition of the two. Okay. It was something like that. So those are a little tricky to perform. Okay. Then let's say that we're doing a plus b plus d. So b plus d will be, this could be seen as b. Then right here we go d. Therefore the resultant will be this vector here. So b plus d right there. If I am to erase everything and then add the a, which is, I don't know, pointing straight up, this is a, then the resultant will be this vertical line that was left over. So something like that. Oops. So that was a plus b plus d. Kind of tough to keep up with, but okay. Now number 70, vector v has the initial point p1 and the terminal point p2. Write it in terms of ai plus bj. Okay, so what we want to do is get the difference between the two components of x and the difference between the two components of the y. So this is what we mean. Let's say that we give this name, this vector, vector v already has a name, so is equal to x2 minus x1 times the I component plus y2 minus y1 of the j component. So that's how we're going to come up with v. So we have 1 minus negative 4, so plus 4, times I plus 2 minus 6j. So this is 5I minus 4j. So based on the 2 points that were given, that's how we come up with vector v. Okay. So 5I minus 4j. Then, if we're looking for number 71, we'll do the same thing. Vector v is equal to negative 1 minus 2I plus 4 minus 4j, giving us negative 3I plus 0j or no j. Just a horizontal vector pointing in the I direction 3 units to the left. Okay. So we're going to find the specified application, or the combination. We're looking for u plus v, so the operation is addition, and all that we have to do is combine the respective parts. So combine the i's and then combine the j values, or the coefficients in front of each, right? So negative 5 minus 2i plus negative 4 plus 7, and that's the j. So this gives us negative 7i plus 3j for the vector components, right? So u plus v is going to be negative 7i plus 3j. Okay? And if we are subtracting, we're still going to do the same thing. We are going to subtract the I components plus the j components subtracted. Okay, so we have negative 5i minus 9j. Okay, so now the following is going to be v minus u minus w. So let's do some order of operations and do what's inside of the parentheses first. So u minus w. So 10. Actually, it's the other way around. We have to do 1 minus 10i plus negative 5 Number 73, we're doing u minus v. So we subtract negative 10 minus negative 5, which becomes positive 5. So negative 10 plus 5, I plus negative 2 minus 7j. That all equals negative 5i minus 9j. Okay, so the first component minus the second one, and then the first j component minus the second one. So we get negative 5i minus 9j. The following is number 74, and we have v minus u minus w, but u and w are inside the parentheses, so we have to do that first. So u minus w is equal to 10 minus 1 I plus 1 minus negative 5, and that's all the j components. That is all equal to 9i plus 6j. Okay, so all of that, we're going to do v minus this. Okay, so what do we have? We're going to have negative 5 minus 9i plus negative 8 minus 6j. So that is going to be negative 14i plus, actually, minus 14j. So overall, we're going to get negative 14j minus negative 14i minus 14j. Okay. Find the difference between v and u, and then find its magnitude. So let's do the inside operation first. So v minus u is going to be equal to negative 10 minus 6i plus negative 30 plus 2j. That's going to be negative 16i minus 28j. And the magnitude of that will be equal to the square root of the sum of those two things squared. We'll get something like 32.25. Okay. Okay. Use the given vectors to find the specified dot product, right? So we're saying the dot product give us a scalar as the answer. So how do we do this? Multiply the first components or the I components and then add them to the j components. So 11 times 10, 110, negative, minus 28, right? So total will be negative 138. Okay. Find u dot product w plus v dot product w. Okay, so u dot product w will be negative 5, negative 3 plus 3 and 12. So 15 plus 36 is 51. All of that plus VW Now this will be negative 5, negative 3, plus negative 6, and 12, right? So negative 5 times negative 3, all of that inside the parentheses, plus negative 6, 12, and we get negative 57, so 51 plus negative 57 gives us negative 6. Okay. We'll skip 78 since it's very similar. Now, number 79, we want to find the angle between the given vectors, and we want to round to the nearest tenth. Okay, so important, right? How do we figure out the angle between them? We have some different formulas for it, but overall, right, theta is equal to cosine inverse of u dot product v over the magnitude of u times the magnitude of v. Okay, so let's do u dot v, and let's see what we get. So negative 1 times 6 plus 5 times negative 4, so negative 6 plus negative 20 gives us negative 26. Then we have to find the magnitude of u, which will be the square root of 1 squared plus 5 squared, which is square root of 26. So we'll keep that on the side, square root of 26. Then the magnitude of v will be square root of 36 plus 16, right? So 42, 52, square root of 52. Can 52 be divided by any perfect? Yep. So 52 is the same thing as 2 square root of 13. We can probably use it better if we do it like this. Right, so 2 times, well, square root of 2 times square root of 26. So if we put all that together, okay, here's the deal, right? We have theta is cosine inverse of negative 26 over square root of 2 times square root of 26 times square root of 26. So when we multiply two things that are equal under the radical, they cancel each other out. Okay, and we'll get something like this. Theta is equal to cosine inverse of negative 1 over square root of 2. Okay, why was that? Let's take a step back. So we'll get negative 26, and underneath we'll get square root of 2 times 26, and the 26 we're going to cancel out, so we have cosine inverse of 1 over negative square root of 2, and that is equal to cosine inverse of negative square root of 2 over 2, and theta will be 3 pi over 4. Okay, so the angle between the two, and if we want to give it in degrees, then it's going to be 125 degrees. Okay. Number 86. We want to decompose V into vectors, into two vectors, V1, V2, where V1 is parallel to W and V2 is orthogonal to W. So this is asking us to do a projection. So right, we're trying to figure out how much of V points in the direction of W. So in order for us to do that, we need to bear in mind what is a projection. So projection of V onto W is the dot product of V and W over the magnitude square of W times vector W. So let's go ahead and compute those different pieces. V dot W will be 1 times negative 2 plus 4 times 1, and that will be negative 2 plus 4, and that is equal to 2. Cool. Magnitude of W will be equal to negative 2 squared plus 1 squared, which equals to square root of 5, and then the magnitude of W squared will be square root of 5 squared, which is 5. So we pretty much have everything. We have 2 over 5 times the vector W, right? So 2 over 5 times negative 2i plus j, and that gives us negative 4/5 I plus j. So this is the projection of V onto W, but more importantly, this vector we're going to call V1. V1 is parallel to vector W. Okay, that is the vector that is parallel. So how do we find the one that's orthogonal to W? We have to do the original vector V minus V1 in order to find some new vector, which we'll call V2, and then V2 will be orthogonal to vector W. Okay, so we'll have I plus 4j minus negative 4/5 I plus, and I think I made a mistake over here, should have been 2/5 j, so plus 2/5 j. Okay, so we'll have I plus 4j plus 4/5I minus 2/5j. That was V minus V1. Okay, so once we have that, we can combine like terms. And so we have 5/5I plus 4/5I plus 20/5j minus 2/5j. And when we combine like terms, we have 9/5I plus 18/5j. And that will be equal to V2, which is the vector that's orthogonal to W. Okay, so hopefully you were able to follow that through, and just understanding the two different pieces that go into figuring out the vector parallel and the vector orthogonal. Okay. 88. A person is pulling a freight cart with a force of 53 pounds. How much work is done in moving the cart 70 feet if the cart's handle makes an angle of 23 degrees with the ground? For this problem, we are looking for work. Okay, work is defined as the magnitude of the force times the distance, or the magnitude of the distance, times cosine of the angle that it makes with the horizontal, or with the ground. So in this problem, we're given that there's a force being done of 53 pounds times the distance. Well, the distance is between point A and point B, so 70 feet is given as the distance that we're moving it. And then we're told that it makes an angle of 23 degrees with the ground, so cosine of 23 degrees. Okay, so we are pretty much done. We just have to compute the three different values, and what we get is that we have done work of 3,415 foot-pound. Well, the units are just this, foot-pound. Okay. Problem 89. Find the work done by a force of 2 pounds acting in a direction of 40 degrees to the horizontal in moving an object 4 feet from point 0, to point 4, 0. Once again, we're looking for the work, and work is the magnitude of the force times the magnitude of the distance that is being moved times cosine of the angle that the force makes with the horizontal. So once again, pretty easy here because it's given very explicitly 2 pounds is the force, so 2 times. We're told that we're moving it 4 feet, so that is a distance, and then cosine of 40 degrees. Okay, multiply that together, so we have 8 times cosine of 40 degrees, and we have done a work of 6.13 foot-pound. (91) We were looking at the matrix 9, -10, -9, 0, 7, -11, -5, -6. So we're asked to give the order of the matrix and identify the given element in the matrix. So find the order and the specified element. So remember, order, it's just another word for dimension. And so the order is how many rows by columns does the matrix have? And we see that it has 2 rows by 4 columns. Therefore, the dimensions or the order of the matrix is a 2 by 4. I guess it doesn't have to be in parentheses, but the order or the dimensions is 2 by 4. Now, remember, when we're given an element in lowercase with 2 subscripts, we know that the first one tells me the row and the second one tells me the column. So if I go to row number 1, column 2, element A12 is equal to -9. Therefore, that is the specified element on the matrix. Number 92, we're given the following matrix. And we're asked to find the values for the variables so that the matrices are equal. Okay. First of all, both matrices have to be the same dimensions. And if they are, then we can go ahead and solve the problem. But if they're not, then we shouldn't even continue. We just say that they're not the same dimensions. We can't figure out the value of the variables. But in this case, we have x plus 3. It's in the spot 1, 1, but so is number 6 on the other matrix. Therefore, they must be equal to each other. Well, if we solve this using algebra, we get that x is equal to 3. Perfect. Then we have y plus 4 is equal to -4. And if we solve this, we get that y is equal to -8. Then we have -7 equals to z, and we're done. We have found the 3 variables that are unknown. Okay? Number 94, we are given matrix A as -1, 3, 0, 4, 9, -4, and B as 7, 2, 17, 4, 3, and 2. What we want to do is find matrix A minus matrix B. Again, before we start the problem, we want to make sure that they're both the same order or the same dimensions. We realize that yes, they're both the same order. Then we can begin. So A minus B is equal to -1 minus 7, and I'm just going to write in the elements that go into each spot, so simplify that afterwards. -1 minus 7 is -8. 0 minus 17 is -17. 9 minus 3 is 6. 3 minus 2 is 1. 4 minus 4 is 0. -4 minus 2 is -6. And therefore, we have found A minus B. Okay. So, subtraction, they have to have the same dimensions in order for the operation to be performed. Number 95. We are given two matrices, A and B, and we have 7, 6, 3, 14, 4, -1, -3, 4, 3. And we're given B as 10, -3, 2, -6, 0, 5, 1, 3, -4, and we want to find A plus B. Again, addition and subtraction of matrices can only be done by matrices that have the same order or the same dimensions. Okay, so let's go ahead and begin. 7 plus 10, 6 plus -6, 3 plus 1, 14 plus -3, 4 plus 0, -1 plus 3, -3 plus 2, 4 plus 5, and 3 plus -4. Again, that's the elements that are in the correct spot, I guess you can say. And then I'm going to further simplify it a little bit more. So 17, 0, 4, 11, 4, 2, -1, 9, -1. Okay? So addition is just straightforward. You just add the corresponding elements that are in the same spot in each matrix, and then you're good to go. Okay? '96. Again, we have matrix A, and in this case we have a 2 by 2, which is a 2, 3, 2, 4. So those are the elements in this 2 by 2 matrix. B is the following: 0, 4, -1, 6. So we are asked to find 3A plus B. So we have a combination between scalar multiplication and addition of two matrices. So what we can do is multiply everything in A by 3. So 3A will look like this. So 2 times 3 is 6, 9, 6, and 12. Now that we have that, we can add it to the matrix B. Once again, they have to be the same dimensions. So 6 plus 0 is 6, 9 plus 4, 13, and then 6 plus -1 is 5, and then 12 plus 6 is 18. Okay? Number 102, we're trying to find the product of matrix A times matrix B, if possible. So it may not always be possible to find the product between two matrices. First, let's write the dimensions of A. Matrix A is a matrix of 2 rows by 3 columns. Matrix V is a matrix of 3 by 2 columns. So one trick is to write the dimensions of the first matrix that you're multiplying times the other matrix that you're multiplying, and if the inside dimensions match, then you can do the multiplication, and the outer 2 will be the resulting dimensions of your matrix. So 3 is equal to 3, so yes, we can perform the multiplication, and the size of the matrix that we get will be a 2 by 2. Okay, so let's do it. Be real careful when you multiply things, and we'll start out with the first row by the first column. So we'll get 3 times 1, which will be 3, 3 times negative 2, which will be negative 6, negative 2 times 0 will be 0. Okay, that is the first part of the product, or the first element. Then we'll do the element right below, and we have 3 times 2, which is 6, negative 2 times 0, which is 0, and then 0 times 5, which is 0. Okay, then let's work on this element right there. So it's going to be the one right here times the top, and we'll have 0 times 1, which is 0, 1 times 3, which is 3, and then 5 times negative 2, which will be negative 10. Okay, then we'll do the bottom right. 0 times 2 is 0, 1 times 0 is 0, and 5 times 5 is 25. If we simplify this, we'll get negative 3, 6, 3 plus negative 10 will be negative 7, and then the denominator will get 25. So that is the product between A and B for the two dimensions.